vector, right? So to construct the gradient vector, what do you need to find? All of the
fx, fy.
What are those called? All of the partial derivatives. So you need fx, you need fy, and you need fz. So once you have fx, fy, and fz, each of those is going to change depending on what point you're at, correct?
Yeah.
So you have two different points, so you can plug in at, let's call this point, I don't know. Let's just call it point A and point B. Can you find different gradient vectors at each of those points? Correct. Now, what is directly implied? Oh, they even say, you almost always when they use U, what do they mean? Unit vectors, right? So are your gradients necessarily unit vectors? No, they're not. They are not. What?
They can be scalar multiples of any.
Correct, yeah. So the idea here is you're going to find fx, fy, and fz. You're going to plug in both of those points. You're going to get a direction for at each point, and then you're just going to divide by the, how do you unitize a vector? You divide by the magnitude. Yeah, you divide by the magnitude. What is fx going to be?
2x.
Yep. What is fy going to be? Negative z to the what? Negative 2, right? Correct? There's a negative in front. It's just the constant. It's what's changing. If y is the only thing changing, it's just the coefficient in front of y. What's the coefficient in front of y? Negative z to the negative 2. And what's fz going to be? Yeah, so if you do this out, you know, if you actually have to think about this one a little bit. You have x squared minus yz to the negative 2. If z is the only thing changing, what's going to happen? This is gone, right? Correct? So you're going to end up with negative, you're going to end up with positive 2yz to the what? Negative 3. So you get 2yz to the negative 3. Does that make sense?
Yeah.
Correct. So now, because it was negative out front and then this drops to the front and then it makes it positive. Okay. So now though, you have to find those at each of the points, right? Yeah, okay. So at point A is 0, 0, 1. What are we going to end up with? 0, negative 1? Yeah. Negative 1 and what? 0. Does this make, are you with me so far, everybody?
Yes.
We're plugging 0, 0, 1 into those values right there. So, and guess what? What is that? Negative j is a unit vector. So we already have it right there. We're done. Luckily, we're done. But point B is 1, 1, 1, which is 2, negative 1, and 2, right? Like this. Is that correct?
Yeah.
I think so. Right. Okay. So in this case, the vector, our gradient vector is 2i minus j plus what? 2k. But is that a unit vector? No. So we need to divide by, which is what? Which turns out to be 3. Yay! Nice. So our unit vector is going to be 2/3 I minus 1/3 j. And yes, there's little hats over these. 2/3 k. We good with that? Before we do this, though, can you tell me what's that general equation for a plane that we like to use? We like z equals plus this is our original one, right? Plus, and it's not exactly in the notation that we're, or excuse me, not the a and b. What do we usually say? Sorry.
Z naught.
X naught and y naught, right? And this is the original way we wrote it before we had partial derivatives. And what was m?
Fu.
Fx, and this was fy, right? So do we have those values?
Yes.
Yeah, we actually have those values. Do we have a point and do we have those values? Yeah, so it's just substitution for part B. Are we good? Are we good with that? Does that make sense? Now was there another equation we could use? Was there any other way that gets rearranged at all? Do you remember?
The A, B, C.
Yeah, there's like, do you have the normal vector?
Yes.
Yeah, so another way to write it was something with A, B, and C. Do you remember what it was? So do you remember what the equation was? A times x naught plus b times y minus y naught plus c times z naught equals, this equals 0, right? Exactly. So either one you can use, it's going to be fine. So actually, let's do one of these out here. So let's use this one right here. Relatively sure that's the case. So which one do you want to do? 0, 0, 1. So what was that gradient vector going to be? The gradient for this one. So at a, which was 0, 0, 1, the gradient of the function was what? Was negative j, right? So what do you end up getting? So let's just plug everything in and see what happens. You get 0 times x minus 0 plus 0 times what?
Y minus.
Y minus what? 0.
No.
Oh, that is the one. That is the actual only value we have, right? What is that? That's negative 1. Sorry. Yep. Plus what?
0.
Z minus 1.
Times z minus 1, right? Equals 0. So what are you left with? Negative y equals 0. Hey, nice. So what's another way to write that? Y equals 0.
That's the XZ plane.
Yeah. Yeah. You found a plane. It's about as simple as it possibly can be. That does not mean finding this is easy. I mean, I personally believe it's kind of hard because it's so simple in a way. Does that make sense? So when we're trying to find these, you could use this one instead. That's fine. That's totally cool. Yeah, Jesse. What are they actually talking about in the context of what we're doing? The gradient, right? Exactly. Because we know that the gradient is at a point is going to be perpendicular to the point of tangency, right? So find all points S where a normal vector is parallel to the xy plane. So what does parallel to the xy plane mean?
It has only Z.
It has only this. It's parallel to the xy plane, right? I think it's the opposite of what you said, right? Because look, if you have z, x, and y, here's our xy plane, right? Like this. So parallel to xy plane means any vector with no what? So with not it's not no z component. What is the z component? With k equals 0. Or not k equals 0. I'm going to be precise here. With k component equals 0. Does that kind of make sense? If you have lots of different vectors pointing in different directions, they'll all be parallel to the xy plane as long as it's not going up or down. We good with that? Yeah. So we're looking for all the gradients where you end up with a z component being 0. So do we have the general gradient here? Yeah, what is it? The general gradient is 2xi minus what? Z to the negative 2j plus 2yz to the negative third k. That right there is the general gradient at any given point, correct? So to be 0 for this part. We want 2yz to the negative 3 to be what? Yeah, you want this right here. Out of this, you want this right here to equal 0. So you want 2y over z to the 3 to be 0. What's the only way for that to be true? That implies, therefore, that implies that 2y has to be 0, which implies that y is equal to 0. So what does that mean? The question asked, find all points on S where the normal vector is parallel to the xy plane.
So it's on the X.
It's the entire, well, y equals 0 is what plane? The xz plane, right here. So y equals 0. What set of points is this? What set of points is defined by y equals 0? The xz plane.